Next up we have modeling and experiments of wet granular flows in rotating drums. Xixing Li.
Hey, good afternoon everyone. I'm Xixing Li from Tsinghua Particle and Combustion Engineering Group of Tsinghua University. And this work is collaborated with my previous advisor and current partner, Professor Marceau at the University of Vermont. And so this is our outline of the talk today: background and experimental observation, and principles of DEM for cohesive particles, and also the DEM simulation results and conclusion remarks. Also, why we started this research? Because sometimes we face the wet materials like oil sludge, sewage sludge, and even some rotor drum reactor is in fact dry and slow pyrolysis to get some energy from some solid fuels, and so it's in Germany this one have been widely used for waste recovery. And also together with Germany, we have developed some process in China by our group and this standby center. So for me, I think for my PhD, we do lots of rotor cane design. Rotor cane design at 2002, I have published a paper on how to design rotor cane use trajectory. The trajectory model to just the geometry analysis and particle trajectory, and to calculate mean residence time and mass flow rate in currents. And also, but finally I found that if we use DEM approach, can have a good understanding of the profile in the current, and then can correct my previous work for the current, the drum design. Also, I think at this time in China, also in some Europe, some people design the new advanced current. They began to use the formula from particle trajectory analysis. And also another field, because from 3 years ago, I just together with Professor Marceau, we began to do the research because the solid, liquid, and gases, and lots of adhesions. The dense suspension, and also the aerosol flow, and also in the co-granular flow, there are similar phenomena is adhesive force. So we just consider this. We use a method of DEM. Previous DEM used big dry particles, but firstly we extend to the microparticles, and then now we just because this project needs, we want to do some research of wet granular materials. And this is a length scale, this is time scale, this is a coal, blood, this is coal and also biomass sand, and different ways we can say DEM. They have lots of application, I think, in these fields. And compared to kinetic theory, they can provide some particle level information. So DEM is just, I think, for microparticles similar to the MD for the atoms, and they can simultaneously solve the large number particle in a periodic cell and in inflow outflow cells. So it can easily, very feasibly. And adhesive force, I think we have last paper on the van der Waals force. We for the fiber deposition in the flow. The dilute aerosol flow deposition, and also electrostatic force is ongoing, and liquid bridge is just only a progress. My current report. And sintering, because our major thermal engineering, we have done lots of high temperature phenomena. We just starting this work and founding of China. And also, firstly, I just back to the wet granular. Because adhesive force, one is from the mellow matter to macro matter particles. Another one, even the mellow matter particles, if they are liquid volume, they will still have some cohesive force. And there is our system at Tsinghua University. This rotor cane, rotor drum, and quasi two-dimensional one. This camera, and this cane, you can see that cane. In fact, the drum is very experiment, just a very small zone here, and so we just use PIV, and my PhD student Liu, together with me, we developed some PIV algorithms for the granular flow, and you can see this publication details. We just use the cross correlation coefficient to find the interrogation window and the method window to use this maximum value and to get the particle velocity, to get information for that. And also we have got to get a granular temperature, but we don't present here today. And for our current, if 60 millimeter and this kin radius, drum radius, and particle is 1.8 diameter is millimeter. And why we select that? Because liquid bridge, there are two classic papers on the liquid bridge experiments for two-particle liquid bridge measurement. And so we just select a same zone of particle diameter. And the filling ratio about I think is 50%, and the rotation rate is 8 RPM. We can see this from that way to here, from just like this way to this. We can see the profile, and it can be classified in two zones. One zone, I think lots of people by Kaka and Dao Ding, they have did lots of paper on this. And that zone, I think some people previously Kaka's work as rigid zone. But in fact, if this is a very slow rotation, I mean 8 RPM, if 25 RPM, in fact, not 20, 55 or 60, 70 maybe, there will be, this deformation will be higher. But for rolling regime, not much. And we can, but still have some transition. But because if you design drum very correctly, you should know this profile very in detail. For me, I just use exponent function here to model this deformation, this small deformation. And for this zone, in this layer, it's just shear flow. It's a classic shear flow. But previously, in Kaka's work and previous publication, they think there is a mass balance between the down and upper flow. But because their work assumed here is the volume fraction don't change much, only very, very narrow layer changes. But in our work, we find that if we use this equation to have balance, that's much difference. But when I'm a little confused firstly, but when I back to let the particle size smaller, just half, this size ratio is 0.015. That's why the 0.8 per millimeter, just 0.03. We can find that for 4 cases, and this is cascading. We don't study it. For our design, fixed to the rolling regime, and we can see that here is not much like the big particles. These big particles, this difference, but for that one, it's much. The algorithm is much better. Why? It's only because for big particles, and we find here the relatively not narrow layer, their volume fraction changes. So there should be some volume fraction. I mean, particle concentration should be modification here. So that's how we can be model more correctly. And then because the today's topic is focused on the wet material, we just add the total sand here. I calculated about 10,500 particles in the drum. And if we use the silicon oil different into it, we can find the angle, the angle of the repose changes. It's increased like this. But also, if we see velocity profiles at the midline. We can at the bed surface, this with under the with it more oil, liquid bridge is a little higher. We can find here is more, and the velocity decrease is only because the particle under async is under the attractive force make the volume fraction more denser. That's why this changes. And also we can this is so the velocity along the along this line, and we still find the decrease. And but for this is 0 is no liquid was it in. And also at different three line, very good. This three line, I mean, even for wetter material, their similarity is very good, and so that's quite good for the dryer and current dryer design. And only higher liquid bridges that's some difference, but for if the liquid is not more and no much difference even. And DM just sorry, I should speak more fast. Sorry. And this is our previous work for the DM for the microparticles, because colliding and necking and shearing and twisting and rolling fraction. But for big particles, according to some experts like ABU, who is Australia expert on DM, rolling fraction and twisting fraction for the dynamic system like current, like drum, not much. So we don't consider for dry particles. And we only consider the colliding and normal force and sliding fraction. And this is the translational and rotational motion of particles. This is the equation. We don't consider fluid force here because this cooling is also can do the fluid force. And DM previous work I don't describe it from the Connor's work. Tsuji lots of work on the granular bulk flow. They also use two theory. One is Hertz, one is more linear, more simple linear work. And but for adhesive particle flows, but very suppose at this time because lots of fundamental work have been done. GCAR model. GCAR model is Johnson is professor of Cambridge. He developed the contact adhesive contact constitutive model of adhesive contact, and also some under the adhesion, the sliding and the sliding fraction and rolling fraction, there still some model can be referred for that. And so this lots of people different ways. Some people go this one is just from DMT, this from JKR. JKR DMT, the difference is only use the elastic displacement to the surface. The surface distance. And JKR this time I think for some is widely used. And what's different with Hertz theory? This is Hertz stresses. This is contact radius. This is just adhesion force. It's in. They develop JKR in this way. And but for liquid bridge force, when you consider adhesion, how do you consider? So not much direct model to GKR and Hertz and DMT, no much one. So we should reconsider this one. Though lots of classical, lots of papers have been done this, but there's still lots of phenomena I think unclear. Just for this is for the Hertz normal force, and this is but our difference here how to consider the adhesive force, just the cohesive force, liquid bridge force here, and this is a normal dissipative force. Some people like use linear model. They don't like the Hertz because they think that it's much easier to consider the dissipation. But I will discuss later. Jeff, Professor Marshall have done a lot to how to relate the dissipation coefficient as the coefficient of the restitution. And it's only because here energy is lost during collision. And so the important is just we should consider liquid bridge adhesion. Because liquid bridge, some people like to use Young Laplace equation to do this work. But for my argued two classical papers, I think these two are very good. And one is for Jonathan Server's group, and one is Peters. From these two papers, we can find some interesting phenomena that here is the skilled liquid bridge force to the surface tension. And we can find even you increase the volume, but the line, the trade-off force with the rupture, with the separation distance, much similar. And when I have a scaling again, just like this scaling, we can find all the line collapse into one for the liquid force. So we need to solve from experiment. We can join some similar theory, but we need to solve the Young Laplace equation directly. So here is only we should have two equations. One equation uses this one, just to predict force. Another one just to predict where the two particles is rupture, is separated. This equation is this. And so we use these two equations and combine with the Hertz theory. I solved lots of work. And so when I do this, I compare this work with if I assume the surface tension equals to the magnitude of the surface energy, we can say that this is JKR. This is JKR. I mean, here is normal force, here is overlap, and separation distance. Here is JKR. Here is DMT. DMT is n at this. But liquid bridge together with Hertz theory is like this. So if we change this the volume, or the surface tension, there is no difference with GKR, and also give us some idea how to treat such kind of isotopes according to the work of van der Waals force. And also we change this the volume fraction, and we find this. This is the difference of the attractive force will be much narrow. So this is just the model, and sliding fraction. And also this one I don't discuss more, but I think sliding fraction at this time, I think even on the DM simulation cohesive materials don't consider very thoroughly like the normal force. That's why even the comparison of the modeling with the experiment are not so much. So the van der Waals force, and I think there are some classical papers for this. But for liquid bridge here, we use this one. But I think this one not so correct, because this one we can use a value like this one, a fixed value. All the normal force can be to the positive, but this one both negative and negative. So lots of changes that. And this are our simulation. The scaling we use drama. We use non-dimensionless simulation. This time scale and particle scale, the fraction, and we set this coefficient at this. We can see our two particle here. We have this we related this coefficient of this equation to the displacement rate, and so we can control the simulation normal force very correctly from this equation. And Jeff has published work in Journal of Computational Physics, and also we can find some people will say elastic, modulus are very important. We also model that we find that if we use this one scaling the overlap and the time, all the line will collapse into one. But also we should select the overlap should be much smaller. If enough smaller for normal force, the effect again is not much. So that one is very important for the use Hertz theory for DM, and also for liquid bridge force. This is we can show velocity here, and if the ratio adhesion to if this one is just the surface tension to the inertia ratio, we can see if this is enough large, and then the particle velocity will adhere each other. But this one will go away, but we set 0.7. This is from coding. And also we do the simulation. Yeah, just like this, quite stable. And also we compare this with, this is a trial 1. We found that for mineral theory, the catalyst selection is much more important to let your, from this one, I have no time, I will say, here, these two difference is important. Here, transition is important, and this three, if this three can agreement, then your modulation is reasonable. So at this time, I think if we, because lots of things, reduce the particle number, I think more and more better prediction of the theory of DM with the experiment can be get. And this when we change the KT and the angle much closer to our experimental is about 30. And so this one much closer, this is too not so good. And so, but liquid bridge currently we do not consider the sliding fraction and the modeling the modeling for the increase angle repulse is not so good till now. But I think if we consider this, it can be becomes better. That's my conclusion remarks. Sorry for a little delay. Okay, thank you so much.
Okay, thank you. Okay, any questions?
Yeah. I guess I'm a little concerned about the role of roughness, because I mean, it seems like a lot of these models of liquid bridging and so forth that are assuming non-smooth particles are going to break down pretty quickly once any kind of realistic roughness is introduced. Have you given any consideration to that issue?
To you mean rough distance?
The roughness, the role of particles.
Roughness, yeah. In fact, for the liquid bridge, we use for our experiment because we use glass bill, and because I think its surface currently is I think its surface not much, the roughness. But for liquid bridge, also I think for the work, for the paper, published paper, I think. Here, sorry. What I consider that is just how to consider the Cadbury force combined with the Hertz theory. But we only find the not from two groups, and I think their experiments have highly cited, and we found if we even in fact how to say even you have roughness, but your magnitude of maximum cohesive force at this point, the scaling is very good. Don't change mass. The volume fraction only changes. What's the volume fraction is changes just line like this. Like this is, but this zone, how to relate this zone to previously existing theory like the JKR and to develop the adhesive contact is still a lot of work we will do. So even for the currently I just find the sliding in the adhesion is much important. But normal force, I think its effect is limited according to my previous work.
I mean, there was about 10 years ago a literature that around the effects of roughness, which are quite observable at relatively small liquid volume fractions.
Yeah.
Possible that you are.
Yeah, but for this one, our experimental is all in this zone. The volume, I mean, this is dimensionless volume, just like this volume to the cubic of the radius, particle radius. So it's much smaller, yeah. But its effect is not so small. So finally, I mean in the current, the particles mass is 70 grams, but if you add 0.1 into it, and the angle and finally it changes. So that's a problem. This we just do experiment many times and find this. So experiment, that experiment is much clear for this one. Okay, you can see this. If you can see the oil, in fact, you can see by eyes, but its effect on the ambulatory pulse is much higher. But in fact, its volume not much. It's only 0.01, 0.0001. I mean,
And it's hard to account for that linear behavior unless you include the effects of roughness.
this one. Yeah. It's we only know this value, but I can only estimate this value, but I cannot accurately calculate which value. You know, because your liquid, you have all the oil mass, and also how many liquid volume will be formed of these 10,000 particles. So that's not easy to calculate. I can only estimate it, but I cannot calculate precisely. Yeah.